Well, welcome back, everybody. Today is Pre-Calculus Day 5, and we're going to talk about lines. And so let's recall some things. So we know in the plane that 2 points determine a line. So maybe I've got some point x1, y1, and some other point x2, y2, and I can draw a line between them. And so we know from previous courses that the slope of the line, or the steepness, is defined as follows. So we use m to denote slope, and that's the change in y's over the change in x's. And so that's y2 minus y1 over x2 minus x1. Okay, and of course, if this number is positive, then reading from left to right, then my line will look like this. If this slope number is negative, then reading from left to right, my line will look like this. So let's actually say that. And so I'll say, yeah, so if the slope is positive, so greater than 0 means positive, then we have something that looks like this. And 2, if the slope is negative, remember less than 0 means negative, then reading from left to right, we maybe have something like this. And 3, if the slope is 0, then we have a horizontal line that's parallel to the x-axis. And then if the slope is undefined, then we have a vertical line. So then we expect something like this. And it's sort of the division by 0 that you would get in the slope formula that makes this undefined. Right, if the x values are the same, then you're going to be dividing by 0, and then you get this situation. Sometimes further on down the road, we'll say this has infinite slope, but for now we'll say undefined. And so I do want to give you a heads up, maybe something you haven't talked about before. And so what I want to say is that slope actually gives the average rate of change of a function on an interval, and that's really, really useful. It's useful in, well, science, chemistry, physics, engineering, economics, business. It's useful in a lot of places. So I want to note that as sort of, again, a little sort of heads up for your future. So slope gives the average rate of change on an interval. Or I can say from one point to another point. And so, for example, say I've got some nice function that models something. Maybe it models profit, or maybe temperature, or something like that. But say I've got some nice function. Okay, so let's say here's my function. This is not a line, of course, but it's just some function y equals f of x. And if I wanted the average rate of change from one point to the next, so for example, if I wanted the average rate of change from here to here, so from x1 to x2 on this interval, that's exactly what the slope of this line is telling me. It's giving me the average rate of change on that interval. So I'll say the slope of this line segment, let's actually be precise. Let's call it L. So the slope of L is the average rate of change of the function and we'll actually see a concrete example of that a little bit later. But I didn't want to wait to show you how useful this is, I wanted to give you again a heads up. Okay, so plenty of the lines that we'll be talking about today are functions, right? These are sort of our simplest functions in some sense. And what I want to do is start to dive into the different types of lines, and I'll try to point out which are functions and which are not functions. So some of the simplest functions or simplest lines would be our constant lines or constant functions. So for example, x equals a constant, so x equals a number. Let's call that number h. Okay, so yeah, just keep in mind that h is a real number. H is some real number. And also, just to tie in from earlier, these are going to be lines that have infinite or undefined slope. We'll dig into that in just a moment. We also have these constant lines of the form y equals k, where k is a real number. And these will have zero slope. And so let's give some examples. So for example, let's say I want to graph x equals 2. So I noticed that y is a free variable, and the way we said we think about this in the plane is that we collect ordered pairs of the form 2 comma y, where y takes on all numbers. And the collection of all of those points is the line that we want to draw. So of course, again, y is the free variable, so you're going to see 2 comma 0, 2 comma 1, 2 comma 1/2, 2 comma pi, all of those are on this line. Since y is free, it takes on every value. Remember what I mean by free? It means there's no mention of it. So the understanding is, since there's no mention of y, it takes on every y value. So that's our line x is equal to 2, because anywhere on that line, x is, well, equal to 2. Well, if I drew this a bit nicer, you'd see this is parallel to the y-axis and perpendicular to the x-axis. And again, this has undefined slope. Sometimes, again, you may hear this has infinite slope. Okay, so one more example like this. So let's say we wanted to graph x equals -3. So here's x, here's y. I'm going to put a little bit of a scale rather here on the x-axis. And on the y, and x equals 3. Remember, y is free, so this is the collection of all the points of the form -3 comma y. So that looks like this. Again, it's parallel to the y-axis and perpendicular to the x-axis. That's x equals -3. Okay, what about lines of the form y equals constant? So for example, let's say we wanted to graph, I don't know, how about y equals 1? Again, x is the free variable, so the understanding is that this line is the collection of all the points of the form x comma 1. X will take on every real number. Any real number you can dream of, comma 1 will be a point on this line. So this line should be parallel to the x-axis and perpendicular to the y-axis. So y equals 1. It's the line where all the y values are 1, and again, it goes through all the x values. X is free or takes on all real numbers. Notice that the slope is 0. And of course, let's do an example where y is maybe negative. Y is -4. Now, of course, I know I picked integers for these. They don't have to be integers. This could be radical 2. This could be pi. We've got a lot of, there's a lot of real numbers out there, right? You've got some options. Okay, so y equals -4. This is the line where all the y values are -4, and x is free. X takes on every real number. And those are our constant lines. Notice that these are functions, right? And these are not functions. Why are these not functions? Because I've got one x input mapping to every real number. So maybe just to tie this in with functions, I think that would be smart. So I've only got one value in my domain, and it's mapping to every real number you can dream of, right? So 1, pi, square root of 2, etc. So that breaks the definition of a function. So that certainly can't be a function. So let's call this the domain, maybe the range. Not a function. Certainly a relation. Remember, relations were subsets of the plane, right? But it's not a function. Here, there's no issue at all. So here, sort of the opposite's happening in some sense, right? So domain, range. Only one number gets mapped to here, right? Only a value 1. But I've got, again, so maybe 1 pi radical 2, -5, etc. Well, this doesn't break the definition of function, right? So every number in here goes to exactly one unique place here. 1 doesn't go to 5 places. 1 doesn't go to 2 places. It goes to one unique place. So 1 maps to 1. Pi maps to 1. Radical 2 maps to 1, etc. So this is a function. Functions, not functions. Okay, so let's start to talk about more involved, sophisticated lines. So what if we don't have, x equals a constant or y equals a constant? What about y equals x? So we'll see later in this course, this is quite an important line. It's actually called the identity line. Y is identically x, but it has for identity has a deeper reason than that when we study something called composition. Okay, so for a little bit, not too long, I'll use a table of values, but it's really not the best way to graph, but it'll sort of get us started here. So the y value is equal to x. So for whatever x I choose, because x is independent, this tells me how to cook up y. Y depends on my choice of x. So if I choose x to be 0, then y must be 0. If I choose x to be 1, then y must be 1, because y is equal to x. So I think we're pretty familiar with this line. It's pretty famous. You probably studied in algebra or algebra 2, etc. And so, of course, 0, 0 is on there, 1, 1, 2, 2. So it's sort of this diagonal. This line will bisect quadrants 1 and 3. And it has a slope of 1. And that's the line y is equal to x. Now here y is equal to minus x, so whatever x value I choose, y will be the negation of that. So if I choose x to be -1, then y must be 1. If x is 0, then y is 0. If x is 1, then y is the negation of that, etc. And if we think about this carefully enough, this actually hints at where we're going when we start talking about translations of functions. So 0, 0. So 1 minus 1 is there. -1, 1. -2, 2, etc. So it'll be exactly this diagonal line. Pretend that's a line. That should be a line. Sometimes that happens. If this were work that I was submitting for a class or something like that, I might use a ruler to tidy it up a little bit, but I think you get the idea. And you'll actually notice that this is just the mirror image of this. So you can think about if I were to take this and reflect it through the x-axis, it would come down here, and that's exactly what you're seeing here. And if I were to take this and reflect it through the x-axis, I would see this, but that's exactly here. Okay, so what's an important form of a line? Well, the first important form is this slope-intercept form. Again, you've probably seen this before. It is a classic. This is y is equal to mx plus b. Or in function notation, we could say that f of x is equal to mx plus b. Right? You drop in an x, you apply the rule, and out comes this. So one thing you have to note with this is that m is the slope, and then we typically say b is the y-intercept, but if I want to be a little bit more precise, the ordered pair 0, comma b is the y-intercept. Right, that's the actual point that's on the graph. So one might say b corresponds to the y-intercept, but this point is the actual y-intercept itself. Okay, and so yeah, so lines of this form, we either have maybe one with a positive slope or one with a negative slope. Let's sort of look at both. So this must be b. That'll correspond to that b. That's the y value that your line's going to pass through. You can convince yourself that's true because if x is 0, this term will vanish and y is equal to b. So when x is 0, y is b. So that makes sense. So this is the line y is equal to mx plus b, or f of x is equal to mx plus b. And then let's assume we go out 1 unit. Okay, so let's just say that's 1 unit. Just going to make a little triangle here. And if that's 1 unit, then this must be m units corresponding to the slope. And m is positive. Okay, and you can see that, sometimes you've heard in previous classes that slope is equal to the rise divided by the run. Well, the rise here is m units divided by the run of 1 unit, and so the slope is m. That's one way to think about slope. Okay, and this is specifically when n is positive. When m is positive, reading from left to right, my line goes this way. And if m is negative, I would have this situation. So again, let's say that's b, and then I'd have some line, maybe like that. That's fine. So it's still y equals mx plus b. But now, when we look here, so let's say that's 1 unit, and that's m units, but m is negative. And since m is negative, well, if I take my rise and divide it by my run, that would be negative. Okay, so that's one form of a line. You've probably graphed in this form, right? You've probably plotted the y-intercept and then did rise over run, up so many units, if that's positive, and then to the right, so many units. There's a second form of a line which is quite useful in calculus and beyond. This is the point slope form of the line. This is the one that I use in practice. And if you really think about it, this is just another way to write the slope formula. Right, this is the slope, point slope form of a line. Imagine if you were to solve algebraically for m, you would divide by this quantity and actually have a version of the slope formula. And so what does this formula do for you? Well, if you know the slope and you know a single point, this will generate the equation of the line with that prescribed slope. and which passes through that point. So in order to use this, you have to keep in mind there's two ingredients you need. And so the name is very fitting. So you need the slope and you need a point. So one mistake students will make is that if they're given 2 points, they'll plug both of the points in here. You want to keep x and y variable so that you get an equation of a line. So all you're doing is you're computing the slope for this, and then you're picking any point that's on the line for this. Leave these alone. Don't plug anything for y or x just yet. So let's see what I mean by that through an example. So for example, I'm going to say find the equation of the line that passes through the points let's say -1, 4 and 3, 7. So if I want to use this form of a line, just think about the two ingredients you need. You need a slope and you need a point. So you might be thinking, which point do I choose? It actually doesn't matter. You can choose either of these points for your single point. Oops, that should be a 1, by the way. So right here, let's fix that, would you? That should be x1, y1 corresponding to x1, y1 here. I just caught that. Okay, so maybe I'll write that a little bit clearer. So x1, y1, just for clarity. Okay, so for that point, it doesn't matter which of these I choose. I'll get the same correct line. Either way, you should sort of check that as an exercise. But either way, I do need the slope. So the first thing I typically do is I find the slope. That's just given by the slope formula. So we know that the slope is equal to the change in y's over the change in x's. But that's exactly y2 minus y1 over x2 minus x1. And so I'm just going to consider this to be x2, y2, just because it's my second point. I'll consider that to be x1, y1. So if I do y2 minus y1, so that'll be y2 minus y1, second y value minus first y value, over x2 minus x1. And of course, watch your double negatives. So that's going to give me 3 over 4. And there's my slope. In the old way of thinking, you can think about that as rise 3, run 4, up 3 to the right 4. Okay, so we've got the slope, check. We need a point. Doesn't matter which I choose. Let's choose the first one. Again, I do have my choice here. Okay, so now that I have m and my point, I can take both of those to my point slope formula. You're going to see m go in here. You're going to see x1, which is this, go in here, and y1, which is 4. That's going to go in here. All right, so let's go ahead and do that. So point slope form, so this will be y minus y1 equals m times x minus x1. We said that y1 was 4. We said the slope we found before was 3/4. And we said x1 was minus, that's going to give me, of course, double negative, so that's going to be +1 again. A minus from here and a second minus here. And so my goal now is to solve for y so that this is in slope-intercept form. So what does that mean for me? Well, I should probably distribute this. So y minus 4 is equal to 3/4 x plus 3/4. And then we should probably just add 4 to both sides because we want to isolate y. So y is equal to 3/4 x plus 3/4 plus 4. Show you a little trade secret for adding fractions here. Let's put that over 1. Maybe I won't get common denominators. I could. Here's some old school 19th century math for you. If I have a over b plus c over d, and neither of these are 0, then their sum is this product, so AD, plus this product, BC, over this product, BD. That's not hard to verify. And so in practice, I use this. I guess it depends on the case. I can't say I rarely get common denominators, but if this is useful and practical and easy, I just do it this way. So I'll say, okay, this is 3 plus 16, so that's, what's that, 19? Over 4 times 1. So product plus product divided by product. Okay, so this is point slope form, right? So this is the, not point slope, this is slope intercept. There we go. So from this form, I actually want to show you a third form. And then I want to give you a heads up on why the third form is nice. So we've got point slope, which allows us to find the equation of a line, which is nice, very, very useful. Use it a ton in Calc 1, 2, 3, and beyond. Point slope, which is sort of that familiar form that you're used to. And then the third form is going to be this general form, which I actually like quite a bit for higher level math. So general form, this is ax plus by plus c equals 0. And so let's actually take this and get this into general form. So I'll just say, maybe as an example, let's express y equals 3/4 x plus 19/4 in general form. So I think the first thing I'm going to do is get rid of the fraction. So I'm going to multiply the whole thing by 4. So that's going to give me 4y is equal to 3x plus 19. Let's see here. I'm going to subtract 3x from both sides. And then I'm going to go ahead and subtract the constant over, right? I want the constant on the left if I'm in this form. And sort of a natural question might be, well, why do we need another form? We were perfectly fine before. Well, it turns out that very often we want to talk about lines in this form because when you, just a heads up for the future, if you study physics or you study higher dimensional math like linear algebra, so I'll say, for the future you will thank you. So for the future, if I have a line that's in this form, so I should say that, so given a line in ax plus by plus c equals 0 form, there's something called a normal vector, which is a perpendicular vector, and it's a really clever and smart way of talking about slope. So I'm going to say n for normal, it's a perpendicular vector. This vector would be perpendicular to my line. It's given just by the coefficients of the variables. So it would be a comma b. And what that allows you to do is look at that at an instant and know the slope, know the tilt without having to do any sort of work. It's very nice. It's also nice because when you deal with things that are higher dimensional, so instead of lines, maybe you're dealing with planes or hyperplanes or, larger dimensional planes, the normal's not going to change. So this concept stays the same. And there's no analog for the slope formula in higher dimensions, not in the same way. So we start encoding that information with vectors. You don't have to understand this now, but it just does, it gives you a heads up on why would we even consider a third form that right now seems useless, but turns out to be very, very nice in the future. And that's why. Thinking in this way allows us to encode the idea of slope in higher dimensions. All right, so let's do a little recap before we go further. So we have the slope-intercept form. We said that was y equals mx plus b. And with that, we said that m is the slope, and that's given by the change in y's over the change in x's. That's y2 minus y1 over x2 minus x1. Okay, so that's the slope. And then we said that the y-intercept was the point 0, comma b. So b corresponds to the y-intercept. Okay, so that's form 1. It's probably the form you're the most used to using. The next, which is very, very useful, and again, you'll see this again in calculus, is point slope. That's y1, I'm sorry, y minus y1 equals m times x minus x1. And again, slope, that's our old friend here. That's m, which is the change in y over the change in x's. That's exactly y2 minus y1 over x2 minus x1. And then for x1 and y1, we can really just take any point that's on the line. So if I was in a situation where I knew 10 points and I didn't know what to do, you could choose any of those 10 points, and that will be just fine for your point. And again, that corresponds to x1, y1. And then there's this last form we talked about, this general form. And that seemed a bit, at first, if you don't know enough math, which is normal, right? It's a process. It seems like this extra useless form, but it turns out not to be useless at all. And so for the future, we said that n equals the vector AB is perpendicular, aka normal, to the line. And that was important because that encodes the idea of slope. You'll see that in the future. And these were of the form y was equal to k. It makes sense. The y value would be fixed if that was horizontal. And the thing we want to note here is that the slope is 0. That makes sense. If I go to look at the slope formula, well, the change in y's, that would be k minus k. So that'd be 0 over the change in x's, which yields a slope of 0. And next for our vertical lines. Now for your vertical lines, the x value is fixed. So this will be x equals some constant h. And the thing to note here is that the slope is undefined. That makes sense, because if you look at the slope formula, you'll have the change in y's divided by the change in x's. But x is constant, not changing, so you're dividing by 0. So you want to note that the slope is undefined. Okay, so let's look at an application to finding average rates of change. All right, so let's say that University X has an enrollment actually let's say had an enrollment of 36,531 students in 2007, and let's say University X had an enrollment or has an enrollment of 48,673 students in 2020. So A, so what was the average annual change in enrollment from 2007 to 2020? And then B, write the equation of the line that represents the given data. And then let's say, what is the slope? And what is the interpretation of the slope relative to this exercise? Well, let's say, what does the slope tell us in this problem? Okay, so first we want to find the average annual change in enrollment from 2007 to 2020. By the way, pause here if you need to. This would be a good time. Okay, so let's go for it. So let's collect what we know. Okay, so let's let X be the year and Y will be the enrollment. So in 2007, we had an enrollment of 36,531. And then in 2020, we had an enrollment of 48,673 as given in the problem. And let's just note that the average annual change is equal to the average rate of change from X equals 2007 to X equals 2020. Well, that's given by the slope. So average rate of change is given by slope. So yeah, let's compute that. So the slope is the change in y's over the change in x's. But the change in y's here, so that's exactly 48,673 minus 36,531. There's my change in y's. Well, my change in x's, so that'll be 2020 or 2020 minus 2007. And so taking differences, I get 12,142 in the numerator over, it looks like 13 in the denominator. And that's exactly 934. But remember, this is a rate of change, so it has to be something per something, right? Because it's a rate. And so what makes sense in this case? Well, we're talking about enrollment per year, so this would be students per year. Okay, and that makes sense if you look at your y's correspond to students, your x's correspond to year, and that's this per this. Okay. So yeah, on average, it looked like between here and here, on average, I increased 934 students per year. So let's give the corresponding equation of the line. And let's use, how about point slope? Okay, so let's see what we have here. So yeah, there's two ordered pairs. There's one ordered pair here. There's a second ordered pair here. Doesn't matter what you choose. Let's just choose the first one. Okay, so y1 will be this, 36,531. M, our slope, we found to be 934. Remember that correspond to the average rate of change. And then x minus x1, well, x1 here is 2007. And now we just use algebra. So let's use the distributive property. So y minus 36,531 equals 934x minus, looks like 1,874,538. And then we just want to isolate y. So let's add this quantity to both sides. So I'm going to add 36,531 to the left. And I'm also going to add 36,531 to the right. So this gives me my line, which models my data. So y is equal to 934x minus 1,838,007. And so what does this line do for us? Well, you pick a year. How about say I'm particularly fond of the year 2009. If I pick the year 2009 for x, this will estimate the number of students, the enrollment, based on this. Okay, so there's a couple very interesting properties of certain types of lines that we need to investigate. So these are important geometric properties. And they're not obvious. We often have to sort of separate the idea of being familiar with something with it being obvious. Obvious means that you know it beyond the shadow of a doubt. You can mathematically prove it. And sometimes we mistake familiarity with something being a mathematical truth. So yeah, important geometric properties. So one, so if two distinct lines are parallel, then they have equal slope. And two, if two distinct lines are perpendicular, then the product of their slope is -1. That's the same thing as saying they have negative reciprocal slopes, right? Why is that? Why is that equivalent? Because if I say m1 times m2 is -1, then m1 is equal to the negative reciprocal of m2. So these are properties you've heard of before, but today we're going to prove them with a bit more care. So let's prove the first property. So if two lines are parallel, then they have equal slopes. So if L1 is parallel to L2, and M1 is the slope of L1, and M2 is the slope of L2, then M1 equals M2. Okay, so we're going to prove this. Parallel lines have equal slope. Okay, so let's start with two parallel lines. So let's say this is line 1. And let's say line 1 is given by the equation y equals m1x plus b1. And we're going to choose L2 so that it's parallel to L1. And so let's say that L2 is given by y equals m2x plus b2. And so I'm going to say, well, assume, so for this proof, let's assume that L1 is parallel to L2. Well, by definition of parallel lines, they have no points in common. So by definition of parallel lines, L1 and L2 have no points in common. And so let's do an investigation. So what if we were to look for points that were in common? So we know that there's not. Let's just play a game. Let's see what happens. So I'm going to say we investigate. M1x plus B1 equals M2x plus B2. And so let's do some algebra. Let's get all the x's on one side and all the b's on the other. So essentially, I just want to solve for x, right? So let's subtract this over to this side and subtract this over to this side. So that should give me m1x minus m2x, when I subtract that over, is equal to b2 minus b1. Okay, well, if I want to solve for x, I should factor an x out. So that gives me m1 minus m2. And then I'm going to solve algebraically for x by dividing. So if I divide both sides by this quantity, x is equal to b2 minus b1 over m1 minus m2. But we know that there's no points in common. That means if they have no points in common, that there's no solution. Well, when's the only time there would be no solution to this? Think about how fractions work. Well, if we divide by 0, there would be no solution. And we know that there's no solution. And so I'm going to say, well, since, how do I know there's no solution? There's no points common. To have a solution would mean they intersect. A solution corresponds to a point of intersection. And since they don't intersect, there's no such thing as a solution here. Solutions correspond to points of intersection. So I'll say, since there's no solution, that can only happen, we must have m1 equals m2. So hopefully that makes sense. That proves that if two lines are parallel, again, that means they have no intersection and thus no solution, then their slopes are equal. Okay, so let's look at a couple lines that are parallel. Let's say I have the following. So let's investigate maybe y equals 2x plus 1 and let's see, versus y equals 2x minus 3. So yeah, let's graph a couple lines. So let's put maybe, let's say this corresponds to 1, maybe that's 2, 3. Let's say this corresponds to the x-axis. Let's say this corresponds to the y-axis. And let's just go up by 1. So that's 1, 2, 3, etc. And so let's graph the first line. For the first line, we know that the y-intercept is 1. Right? So, or the y-intercept, this corresponds to the y-intercept. The y-intercept is actually 0, 1. And then for the slope, remember that's rise over run. And since that's positive, I would, of course, rise 2 and then run 1. So that'll be a point on the line. Rise 2, run 1. Okay, so my first line looks like this. Let's see if I can make these a little bit larger. Okay, so there's my first line. And you can see the x-intercept is -1/2 here. Okay, so for the second line, let's say here's -3, so -1, -2, -3. So the y-intercept here would be 0, -3. So this corresponds to the y-intercept. And then from here, again, with the slope, I just want to go, looks like up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1, etc. So my second line, let's see here. Looks like this. Just make the points bigger if it doesn't fit. Best advice I got in high school. Make the points bigger if it doesn't fit. And you can see these two lines have equal slope. They're parallel. Okay, so let's prove that second fact. This is interesting because we'll try and tie in the Pythagorean theorem and the distance formula for the second one. Okay, so for the second one, what do we want to say here? So we want to say if L1 is perpendicular to L2, that means there's a right angle between them, and M1 is the slope, well, not M1, it's the slope of L1, and M2 is the slope of L2. Then the product of their slopes is -1, or that's the same thing as saying they have negative reciprocal slopes when you solve. Okay, so let's sort of draw out the situation and make some clever choices so we can prove this. Okay, so I want to pick two lines that are perpendicular to each other. There's no reason to not pick a line that goes through the origin. I mean, if I have some line that's not through the origin, just translate it. Just move it so it goes through the origin. It's just going to make the problem a lot easier, and you don't lose any rigor in doing that. So let's pick one line through the origin. Let's call that L1, and we'll have a second line through the origin, L2. Okay, so here is L2. And let's very specifically choose a perpendicular here. I can choose any perpendicular line I want. I could choose this one or any perpendicular I want. Let's choose it so it makes our calculation convenient. Again, we lose no rigor in doing this. So let's choose x to be 1. So let's graph the line, or a portion of the line. Oops. X equals 1. So we're going to say construct. If you want to extend it, it's fine, but we only need this portion of it that makes the triangle. So we're going to say construct perpendicular line, x equals 1. Again, if you don't choose 1, just shift whatever you choose to 1 just for the sake of making the calculation easier. It doesn't matter ultimately which perpendicular line I choose, so why not choose a convenient one? Okay, so one thing we want to note is that since these are perpendicular, there's a right angle here. And then since these are on the same straight line, their angles are supplements. So that forces this to be a right angle. Right? They're supplementary angles. So I'm going to say, well, since L1 is perpendicular to L2, we must have, maybe we should label some points as well before we go any further. Let's call this, we want to be able to reference things. Let's call that A. Let's call this B. Let's call this intersection point C. Let's call this D, just for reference. And then let's actually label this point A. Now, keep in mind that L1, we want to think about L1 as y equals m1x, right? B is 0 since it goes through the origin. And L2, let's think about that as y equals m2x. So that labeling is important because I can actually refer to this point. The x value is 1. And then to get the corresponding y value, just plug 1 in for x. So y is equal to m1. This point, same sort of idea. So to get this point, the x value is 1. And to get the corresponding y value, plug 1 in. And so y is m2. Okay, so things are labeled now. We can refer to them in our proof. Okay, so since L1 is perpendicular to L2, we must have, by supplementary angles, that angle ABC is a right angle. Right, 90 plus 90 equals 180, and that's on a straight line. Well, since this is a right angle, this triangle, ABC, must be a right triangle. So since angle ABC is a right angle, triangle ABC is a right triangle. And since triangle ABC is a right triangle, the Pythagorean theorem holds. So if that's the right angle, this has to be the hypotenuse, right? The hypotenuse is always opposite the right angle. So this is leg, hypotenuse. So by the Pythagorean theorem, leg squared plus leg squared equals hypotenuse squared. Okay, so let's set this up. So by the Pythagorean theorem, we have the following. So the length of AB squared, so the length of AB squared, right? That's one of the legs, plus the length of BC squared is equal to the length of AC squared. But can we find the length of AB and BC? Yeah, I can find the length. Isn't the length just the distance given by the distance formula? So by the distance formula, so this is going to be the distance or the length squared. So what is the distance formula? Well, it's the change in x's. So x2 minus x1 squared plus y2 minus y1. Oops, should be a 1. Okay, so I'm just using the distance formula on these 2 points. And if you need a reminder, that's fine. Remember that the distance formula is the square root of x2 minus x1 squared plus y2 minus y1 squared. So yeah, for the length of this, I'm using this point and the origin. Okay, that's a 1 right there. Okay, so now I take care of this, plus the length of BC. So I'm going to use this point and the origin with the distance formula. That will give me the length. So the length squared. Okay, so this is going to be x2 minus x1 plus y2 minus y1 squared. So that gave me this. And then lastly, for AC, we can use these 2 points. So I'm going to use this point and this point. That's the hypotenuse, right? So opposite the right angle. Okay, so I need the length or the distance squared. Okay, so let's see what we have here. So x2 minus x1 plus y2 minus y1. Okay, so the squares and the square roots will cancel, and I'll just be left with what's inside. So here that leaves me with m1 squared, because again, this and this cancel, this still stays. And then again, the square root and the square cancel, this will stay. And then I think I've got a 1 squared and a 1 squared, so that'll be a 2, right? So 1 plus 1 gives me 2. Over here, so what do I have on this side? It looks like I have the quantity m2 minus m1 squared. This will stay because only the square root and this square cancel. So now we just have some algebra to do. So 2 plus m1 squared plus m2 squared is equal to m2 squared minus 2 m1 m2 plus m1 squared. How did I get that? I use this classic, right? So I use this all the time, almost every day. A squared plus 2ab plus b squared. That's exactly a plus b quantity squared. So I just applied this formula here. Okay, so now we're going to do some algebra, and you're going to notice that these terms are going to cancel. These terms are going to cancel. And so I'm left with 2 is equal to minus 2 m1 m2. Divide both sides by 2. So that gives me, or in fact, I could divide by minus 2. And that gives us the result we wanted. And if you want to see it with more clarity, just divide by m2. So this shows that they're forced to be negative reciprocals of each other. So cool, right? The power of careful geometric thinking. It's a beautiful, beautiful thing.